So beyond the 80s music, we're now on to an excellent closing presentation and demo. Sethu Vijayakumar is the director for, co-program director for robotics at the Alan Turing Institute. He has brought a prop, but I think it's more than a prop. I think it's a working prop. So could you welcome him to the stage? But first, I want to say that at the end of this, you can enjoy the demo. We can have some chats and all the rest. At 6 o'clock in the back, Quantum Black is kindly co-hosting with the Alan Turing Institute some drinks. And so that's sort of a natural place to move the conversation onto. I will remind you again at the end, don't worry, but I just thought I'd mention that. So, welcome, Sethu.
Okay, thank you all for coming. It's properly Arctic, and I think I was usually been accused of bringing weather from Edinburgh, but believe me, Edinburgh was much warmer today when I left. So I'm going to try and give you a little glimpse of how AI and data-driven innovation can actually make a huge difference in the field of robotics. And robotics is very topical because we're seeing scenarios, we're seeing examples of where robotics is making a huge difference in various walks of life. And at the Turing Institute, we do not build hardware, but we're looking at problems, data-driven problems that arise out of deployment of robotic platforms. So both the challenges that come out of deploying robots in various real-world scenarios, as well as the new kinds of machine learning problems that you have to solve in order for this deployment to work well. So, as I said, one of the challenges is that robotics is being touted as the next big solution across domains, from classical things like manufacturing and things like industry, where we have seen robotics already make a huge difference, to novel kinds of domains like healthcare, smart cities, and things like areas where humans don't want to have their presence, for example, the inside of a nuclear core. So we're seeing really scenarios where humans don't want to actually go in and intervene, and we need robotics as a solution to be able to achieve some of those tasks that we want to solve. So, and just sort of looking through the areas where we are already seeing a huge impact, we are looking at robotics helping in areas for food security. We have an inverted pyramid in the Western society. So the aging population and healthcare and health challenges are massive in terms of solutions that we're looking for. And we have an ever-growing industrial demand. And the real challenge is to achieve this without destroying our environment. So robotics is playing a huge role in achieving all those goals. But today, I'm going to focus on the last bit, which is sort of safe, scalable, and sustainable infrastructure. So looking at scenarios where robots can play a huge role in taking people out of dangerous jobs. So that's what I mean by robots in extreme environments. So this could be inspecting scenarios where going there can be dangerous, can be dirty, or it can be really hazardous environments. So that's the kind of scenario that we're looking at. And you can see some of the examples of things like inspection integrity and nuclear decommissioning, and these are all areas where you would rather want to take people out of harm's way. So often you see the debate of robots taking jobs, but actually there are some scenarios where you really don't want to be in there. You want robots to solve scenarios, to be in scenarios where humans don't want to go and intervene. So the one question that always gets asked is, why don't we take humans completely out of the loop and get robots to fully solve things autonomously? You know, let's have machine learning algorithms, the AI, do things in a fully autonomous fashion. That's great. I think lots of us are actually trying to achieve that goal in various ways. But the real challenge is that because of all the points that I list here, the noise in the sensing, sort of hard to model dynamics, the complexity of interaction, because of all of that scenario, if we wait for reliable robotic systems to actually work in a foolproof manner, we'll be waiting 15, 20 years. So in my personal opinion, we're going to have to deal with this hybrid scenario, this hybrid setting. So often I give this example. So traditionally, when we talked about robotics, we talked about teleoperating systems. So systems where humans or other sort of elements, you had a joystick where you would use it to modulate and move robotic platforms, and the robotic platforms would respond in a 100% accurate way, respond to you. You now have research going towards more autonomy, where you're putting in significant research into getting robots or machines that can make decisions on its own. But really, as I mentioned, in the next 10 to 15 years, we're going to see something where you have to deal with something in between. This is what we call shared autonomy. So how do we deal with set settings where within a single operation, you're going from teleoperation to autonomy and move the slider across in different scenarios, in different settings? So here's the first example of one of the projects we're working on, in which we're looking at shared autonomy for remote operations. So meaning in scenarios which are dangerous for humans to work in. So we have a big project that we have been funded through the nuclear agency here in the UK, the National Center for Nuclear Robotics. And the aim is for getting robots to work in scenarios where humans have no direct line of sight. There is a possibility of a loss of transmission. There's a possibility of significant noise. And in these kind of scenarios, we want a setting where a robot operates in a remote place. It could be another room. It could be another town. It could be another planet. And the person operating it sees a console like this, where you still have human-in-the-loop behavior, where the person says, this is the task, I want you to pick this up and put it there. So that's the kind of high-level human-in-the-loop decision-making that is done by the operator. But the autonomy, the robot has to still deal with significant autonomy in terms of making local decisions. It has to figure out when to move, how to navigate, how to plan, how to make particular decisions on the fly. And that's the challenge. How can we get reliable machine learning? How can we get reliable data processing to be able to do that so that we can trust these systems and verify such systems in the long run? So what is the science underlying this? So what is the underlying problems that we have to solve from a scientific perspective to be able to achieve something like this? So the first thing is obviously sensing. If you look at if you look at the world through the eyes of a robot, it's going to look something like this. Many of you who work in this area will recognize that this is an RGBD image, which is made of point clouds and some texture information. But going from this kind of raw sensor data to something where you can actually navigate and grasp and manipulate is quite hard. So getting machine learning algorithms to work, for example, in this case, tracking objects of interest in real time, and then doing that, navigating the world and responding to behaviors, so dynamic behaviors in real time, in order to adapt behaviors is quite a hard thing to do. So just building robots, building hardware, is not good enough. You need algorithms that are able to deal with things like occlusion, deal with noise in the system, deal with cluttered environment, and do this in real time. And that's the challenge that we are trying to address using these data-driven techniques. So if you now try to put perception and sensing and control together, we can get fairly complex behaviors that we've not seen before. So lots of new advances in these kind of areas. So for example, about 5 years ago, we took part in the DARPA Robotics Challenge, which is a challenge for robots to work in an environment with lots of clutter, deal with settings of navigating complex terrain. So the next video shows you a lab demonstration of a humanoid robot working in those kind of settings. So in this case, navigating a very complex cinder block. And what you see here is the robot building in real time a local map of the world while doing control navigation in real time. So that's a view of what the robot sees. Believe me, it's much harder for it to fall over than balance very efficiently. And that's the map being built in real time. And in terms of the machine learning algorithms, you break it down into what it takes. You have to deal with reinforcement learning, you have to deal with local perception and vision, and real-time footstep planning. So this is what is required for achieving this kind of very complex task. So this is, we take it for granted when we navigate novel scenarios, but for a robot to navigate over complex terrain, it's a pretty hard task to do. So achieving reinforcement learning, so you've probably seen some other talks also, Google X just out there talking about reinforcement learning to do machine learning for perception. And really, doing all of that in real time in the control loop is a big challenge. And that's what we've been trying to achieve as part of the lab that I work in, as well as part of the Turing effort. So where do we apply these technologies? Where do we take all of these signs, and where are the domains we work in? So these are some examples of the domain that we already work in. So the nuclear and offshore decommissioning, disaster recovery scenarios, collaborative manufacturing, and actually right here in London, there is a big project, there's a big hole that is being dug. Well, it's nearly completed, thankfully, called the Crossrail project. And in the Crossrail project, there's a big challenge. Once a boring machine drills through a hole, you have to, in real time, do a cement spraying to make sure the integrity of the tunnel is not compromised. And for that, you need heavily skilled workers. But if you use technologies from data-driven AI, using real-time sensing, then you can actually create scenarios where a much lower skilled worker can operate a joystick, operating a cement spraying device like that, while ensuring that you're not doing something that's disastrous. So this is the kind of concept of shared autonomy, where you exploit the smarts of the sensing while the intention of the action comes from the human. So it's another example I want to give you is in the area of inspection, maintenance, and repair. So we are constantly building, we are constantly creating complex structures, whether it be underground metros, whether it be high-rise buildings, whether it's mines, and eventually we are getting to a stage where managing the integrity of these structures is getting really hard. So how do we guarantee that the next metro that you take is safe, inherently safe, it's not going to collapse? And it's getting physically impossible for humans to do that kind of integrity and asset management. So what we're doing is we're creating robots that can navigate in complex scenarios. So this is a particular example of a robot navigating in a mock-up of an offshore oil and gas platform. So wheeled robots cannot navigate very complex surfaces, but here's an example of a quadruped robot navigating surfaces that are rather complicated for wheeled robots and sometimes even for humans, because it can be slippery with wet surfaces. So it's navigating and moving sensors around in order to get an idea of the complexity of the surface around it, do asset integrity checks, and report back to the human about intervention. So this is an example of how we can sort of really tackle this kind of problems. And if you again look underneath the hood in terms of what is the science needed to achieve that, one of the things that you need to deal with is in the area of topology. So for example, if you're working with environments that are very complex, you've got to work in environments that have got lots of complex surfaces, then we have to work with bridging representations between robot speak and human speak. So let me give you a very simple example. So if you think about a robot reaching inside a box, you can do it in many different ways. But if you use concepts from topology, then when a box moves, the concept of what is inside and outside the box moves with that topology. So then you can adapt the motion of the robot to this novel environment, novel changing environments. And that is really the challenge of addressing that in real time. So here's an example of a robot arm reaching into a box. Again, as I said, you can do it in n number of different ways. But now, if you try to use this concept of topology, then the concept of what is inside and outside the box moves with the topology. So we can effectively, in real time, replan such a task in order to deal with constantly changing environments. And that's one of the challenges in dealing with real-world environments. And this kind of work we've been using in various domains, for example, in snake-like robots for inspection of various structures around settings like an offshore oil and gas platform, inside a refinery, inside even, so this is an example of an asset inspection inside, and even tool welding and cutting in complex scenarios, and also looking inside an aircraft inspection of aircraft inspection engine. And really, I think earlier you would have to dismantle all of the structures before we actually go and do this. But we're able to do this in such complex environments because of working with topological constructs. So that's the challenge of bringing together planning in real time, the AI and the data science with working in complex environments like this. So the other aspect, which is very important in dealing with this stuff, is working with robots that are inherently safe. So that's the big gap between robots that work in laboratories and trying to put that and deploy this in real-world environments. And one of the things that we've been looking at is working with what's called compliant actuation. So in layman terms, it's putting a spring in between a motor and an end effector so that it's inherently compliant. And getting that to work in real time and addressing some of the challenges is a big push. So again, you saw this robot inspecting structures in offshore oil and gas platforms. Earlier, we would have to separate the human and the robot working separately, but now we can create what we call compliant actuation mechanisms, where in spite of the fact that the robot is so powerful and strong, it is inherently safe to interact with it. And that's the kind of technology that we need to build based on, again, real-time sensing and machine learning approaches to deal with safety in these kind of systems. Again, this same approach can be used in collaborative settings where multiple robots, decentralized robots, are handling or dealing with complex scenarios of, in this case, managing a load in collaboration with another human. So again, the challenge is how do we get robotic platforms to work in settings that are really hard for individual systems to work. So can we get collaborative settings, collaborative robotic platforms to work in real time with real-time sensing? And where does these kind of things go into? So I mentioned getting people out of harm's way, getting people out of dangerous and difficult jobs. So one of the biggest problems in the industry today is worker fatigue, worker injury in dealing with really heavy machinery, heavy equipment. So one of the things we're doing, working with Honda, is to try and work with robots that can do collaborative work. So not just two robots working together, but robots and humans working in collaboration in order to achieve a task, a complex task, so that the robot can do the task of taking the heavy load off the human, while the intention of what needs to be done comes and when comes from the human. So this is particularly useful in high-value manufacturing. So, for example, if you try and get robots to achieve a manufacturing in an aircraft industry, so that's what happens now. That's where we are kind of headed to in the new factories of the future, and this is where we want to go to. So robots and humans working together to achieve highly complex maneuvers and get the best of both worlds. So the humans providing the intention and the robot achieving the precision. And this is where the shared autonomy comes into picture. So we have projects with Airbus and some companies in China, the COMAC in Shanghai, working on this kind of projects. Okay, so another example I want to briefly mention is when we talk about extreme environments, space is another extreme environment. And space is a particularly interesting environment because that is where the human exploration and ingenuity comes into picture. So at the moment, you probably heard the news a couple of days ago that NASA have decided to open ISS for tourism. So I think if you've got £27,000 a day to spend on your hotel charges, you could spend it on the ISS. Great. But actually, the space debris is creating lots of problems. Space debris is creating high risk for people maintaining the ISS. These days, if an astronaut has to do a spacewalk, it's actually they have to find the right time and the right space with appropriate protection. And that's where and it's part of one of the areas where we are trying to push in collaboration with the Johnson Space Center is the journey to Mars, in terms of looking at alternate ways, potentially looking at habitation on Mars. So why do we care about that? With an aging society, one of the crazy thoughts that you might have is as we grow old, living in microgravity may help alleviate some of the problems of living in a full gravity setting like Earth. So if you could create a habitat on Mars, which works as good as the Earth, maybe that's not a bad option for somebody who has problems working or living in an environment with high gravity as Earth. So that's just a vision. But to be able to achieve that, you have to address many problems. One of the small parts of the puzzle is getting a humanoid robot like this working in environments that are built for humans. So here's an example of a humanoid robot that we work with in Edinburgh. It's called the NASA Valkyrie humanoid. And one of the aims is to get it to autonomously navigate, locomote, grasp objects, and do real-time sensing and do all of this locomotion in real time. So again, it's a systems challenge because you have to put together all of that control, planning, and navigation setting in real time. But the real challenge is, can we get this to do it really robustly with minimal human intervention, can be built in significant autonomy into the system that it can work with lots of, without real human intervention. So you'll see in a moment the kind of sensing that the robot uses, and this sensing is, again, exactly the same technology that's used in autonomous driving cars. So here's the robot looking around, building a map of the world, and then using it in real time to navigate. So if we get technology like this working in real time, then we can potentially address some of the challenges that are being faced by autonomous driving cars at the moment in terms of robust navigation and robust people detection, for example. Okay, sorry, this is another example of a robot walking on uneven terrain. So walking on flat ground is easy. Walking on uneven terrain, climbing steps, using real-time navigation is pretty hard, but the science we're pushing is trying to address that. And really, it's not just in space that this technology matters. Making advancements in this area makes a huge difference in terms of taking this and pushing it into things like autonomous driving cars and making behaviors much more reactive in those settings. Okay, so the last thing I want to talk about today is about shared autonomy in healthcare. And for this, I'll need a couple of volunteers because I have a live demo that I want to try on you guys, okay? So in healthcare, again, it's the same challenge. We are never going to get to a stage where we will have the need for fully autonomous robotic platforms. And often in healthcare, we're never going to the scenario where we will have 100% teleoperation, because typically robots will be needed in scenarios where people have lost certain ability, either physical ability or some neural degeneration or some sort of other kind of illness. So you will always be in the scenario where we are having this hybrid setting. And that's where the challenge comes in. How do we address, how do we deal with this kind of hybrid shared autonomy setting in sort of healthcare settings? So we've been working with exoskeletons, both upper limb and lower limb exoskeletons. So here's an example of some video of some work we've been doing with amputees, with the NHS, with the National Health Service, on using prosthetic hands with shared autonomy for grasping and manipulation of objects. So what's important here is that it's a three-way communication. The human is still deciding what to do when. Significant autonomy in the platform, or in the robot hand, is actually doing some of the pre-shaping of the grasps, and then the human control does the rest of the shaping. So we're going to try and see this in action. I've got this prosthetic hand along with me, so we're going to get a couple of volunteers to come up and test this technology live on the stage. So can I get a couple of volunteers? Okay, I've got one here and one there, right in the front. Okay, if you want to come up. If you want to come right up to the stage. Yeah. So, I'm going to get you to wear this. Okay. Is that okay? Yeah. And I'll need you to unbutton your cuff because I'm going to attach the sensor to you there. Okay. Yeah. It's heavier than you think, so you may want to use your other hand to support it. Okay. Yeah. Okay. So if you want to come around here. Actually, I need to speak into the mic. Sorry. So that's okay. Do you have a handheld that I can? Okay. In the meanwhile, so what you're seeing here is the prosthetic hand that's being used on these amputees, and this is a little mock-up for wearing for sort of healthy patients to wear, and this here is an EMG sensor. that actually senses the muscle activity of the person wearing this. So we're going to get you to
Testing.
Perfect. Okay, great. Okay, I'll need an object to grasp. Let me. No, that's too small. Too hard. Yes. You can find. I think I bought a ball.
Was viele Fotos jetzt. Was viele Fotos. Wie sieht's aus? Alright. Wie sieht's aus? Das geht jetzt nicht mehr.
Okay. So what we're going to do first is I'm going to turn the hand on, and we're going to see if you have a pulse. Okay, if you now want to try and move your wrist, just your wrist left and right. Okay, again, yeah. All the way, one, yeah. And the other way. Okay, okay, yeah, try again. Okay. Great. So now you can see this. So if you kind of lift it up, so that the rest of the audience can see it. So he's now controlling the robot hand using the muscle activity on his hands, and effectively he's just sending the open and close signals, and the robot hand has the smarts to figure out when each of the fingers should stop closing. So for example, if I now put this in there, and if you try to grasp it, you can see the individual fingers. Oh, okay, try. Don't co-contract, so be relaxed, and then try and go one way. Yeah. Ooh. Okay. Try again. Okay, try again. Great. You're co-contracting, I think, but yeah, go again. Okay, try again. And the other way. Okay, try again. One more try.
Huh?
We try changing the polarity. Try again once more. That was rude. Okay, go for it. And the other way. Okay. No? Let me try it. So it takes a bit of practice though. So. Yeah.
Yes.
So I think you just have to sustain the thing. So what you can see here is now that the individual fingers decide to change the mic. Yeah. Sorry, thanks. So the individual fingers decide to adjust to the shape. If you can grasp that ball for me, is that okay? Yeah. And then we try and put it in there. So you can see that the individual fingers decide when it should stop closing. So that's an example of, not quite. Yeah, good try. So I'm going to try and show you one more thing. I don't have my phone on me. No, hang on. Yeah, great. No. I needed my phone actually. So it's actually up down there, charging. So. Can you grab my phone? So one of the things.
What do you need?
Is just the mic.
Of course.
So you've seen here that I am sending the open and close signals, and the smarts in the hand is deciding to when to stop closing. And one more thing we're going to try is now connect using Bluetooth to this device, using my phone to this device. Okay, so let's try that. And once we have that, okay, it's connecting, and what we can do is we can do pre-shaping of the grasps. So I can now change the shape of the pre-grasp using this mobile phone. So basically, it's a three-way communication between the human and the smarts in the hand and the device. So for example, I can now change it to something called the credit card grip. So that's a credit card grip. And you can see that it's changed the credit into a different mode. So essentially, here's an example of a three-way communication between a human hand, the smarts in this, and the device. And it opens up all sorts of questions in terms of security and how to deal with stuff in real time. How do you ensure that nobody can hack into a device like this? So thank you very much for volunteering. You guys have been great. No, I think getting it to work without any training is a pretty hard thing. So well done. Okay, good. So the same stuff on the sort of upper limb stuff. We're also doing some work on lower limb prosthesis. So exactly the same story, but now we've also got some work on lower limb prosthesis. So here's an example of a person wearing a lower limb prosthesis, and again the same story of shared autonomy, where there's partial input from the human control system while the person is walking. So the exoskeleton, the assistive device, applies forces on the person's legs while while the person is walking. So in case there is a propensity to fall, in case there is fatigue, it can help a person deal with that. It's not just that. So in collaboration with the Johnson Space Center, we've also devised a new use for this exoskeleton. If you change the sign of the assistance from positive to negative, if you make it a resistive device, it's a great tool for preventing muscle atrophy for astronauts on the space station. So at the moment, they take a huge, big rubber band and they tie themselves onto a treadmill for walking. Here's an example of using this as a device to now do resistive activities. So basically, all the stuff that I talked about in terms of the technology, there are some interesting debates we need to have in order to progress this further. So great technology, lots of work going into good science, lots of good hardware, good science, but still when we try to take this technology and deploy it in the real world, there's still many, many aspects that we need to address. So the moral and ethical decisions about use of robots in certain scenarios. Security, I just gave you an example of how people could hack into a medical device or a prosthetic device and potentially, change what you do. If something goes wrong, how do we decide who was responsible for that? Whether is it the human, is it the robot, or is it the manufacturer of a sensor? How do we deal with that responsibility, that causal inference? Transferring control. When, how fast, how long? How do we deal with these questions of transferring control? And finally, learning systems. It's a great boon to have machine learning, but the moment you've got learning systems, getting really robust, verifiable systems get much harder. So these are the kind of questions that we're addressing at the Alan Turing Institute at the Robotics and Autonomous Systems program. So one of the things we are dealing with is, so one of the visions is to create a world-leading scientific program for dealing with unique challenges that arises from and towards deployment of robotic platforms. So you saw some examples of robotic platforms, but there are so many open questions that we need to address before it's ready for deployment in the real world. And that's what we're trying to address at the Alan Turing Institute. And we do that by using, funding core science, working with industry, with lots of companies like Hitachi, Toyota, Honda, Dyson, DeepMind, and we also work with living labs in order to do practical proof of concept deployments in several of these areas. And again, if any of you are interested in working in these areas, please do get in touch with us. Currently, the program addresses three main sort of strands: scalable algorithms under constraints, multi-agent computations, verifiable, robust, explainable decisions for the robotics and autonomous systems domain. So these are the kind of areas we're currently working on. We're looking for people, partners, to collaborate in these areas, and we would love to talk to anybody who's interested in these areas. And finally, I mentioned living labs. So spread across UK, in Edinburgh, in Bristol, in Oxford, we've got various places where we're actually de-risking technology using living labs across different environments. I've talked only about the robots for extreme environments today. You've got other things for robots in healthcare and assisted living, etc., going on. This kind of effort is going on across these domains. So thank you very much for bearing with this cold and being a great audience in terms of trying out the live demo. I'm happy to stick around for a while if you want to get up close and personal to some of this actual device later on. But for now, thank you very much. And if you have any questions, I'm happy to take that.